Good day all and welcome to my channel. Today we'll be looking at a topic in chemistry known as chemical equilibrium. Now, many students they have issues when it comes to this area of chemistry, but I will try my possible best to demystify the topic very well so as for students to understand better. So you just follow the series as I run through. On the board, we're having the topic chemical equilibrium. The word equilibrium means balance. That's what it means. It means balance. All right. And when you say a system is balanced, it means that you can say the system is at equilibrium. And looking at equilibrium as a topic to chemistry, then we should be considering chemical reactions that undergo chemical equilibrium. Not all reactions in the world of chemistry undergo chemical equilibrium, only some of them. In the initials of chemistry, we have different types of chemical reactions. We have the combination reaction, we have displacement reaction, we have redox reaction, we have double decomposition reaction, reversible reaction, and most of the reactions in the world of chemistry falls under the irreversible reactions. In this case, we will be having irreversible reactions to appear or to undergo chemical equilibrium. The reason is because irreversible reactions, they are simply reactions that only proceed in one direction. And the implication of that is the reactants react completely and they will be completely used up to produce products. Generally, in chemical reactions, we are having the left side and the right side. Now, in the left side, we are having the reactants, and at the right side we are having the products. All right, if I write a reaction like this, A plus B to give C plus D, in this type of reaction, this is an irreversible reaction because the reaction is only proceeding in one direction. Now we can call A and B the reactants and we can call C and D the products. But looking at this reaction, it cannot exhibit chemical equilibrium. The reason is because when you start up the reaction, you'll be provided with A and B as your substances that you want to start the reaction with. And then when A and B react, they form C and D. And it gets to a point whereby we no longer be having A and B in the medium. Why? Because A and B will completely react and completely be used up to producing C and D, which are the products. So at the end of the reaction of irreversible reactions, you would only be left with the products and not reactants. But take a good look at this one. A plus B to give C plus D. In this case, this and these reactions, they are totally different reactions. This reaction is a reversible reaction, then while this one is irreversible. This reversible reaction implies that you are going to be having both forward and backward directions, meaning the reactions are proceeding in two directions. Maybe you are starting with your A and B. When you start with A and B, what happens is this: they will react, but they will not be completely used up in the process. When both of them react, they form C and D. And almost immediately, I will use the word simultaneously, this C and D, some of them that are produced, will now react with themselves to produce A and B in return. But at first, the reaction rate in the forward direction is faster. Why? Because you are having A and B being provided as the reactants to starting up the reaction. And at some point, when C and D are being formed, they would react in turn to form A and B. But the backward reaction will be slow at first. But it gets to a point whereby they are trying to struggle like a tug of war. They are trying to struggle to, attain this balance. That's where the chemical equilibrium comes in. And when they attain balance, what happens? Then you will not say that indeed the forward reaction rate and the backward reaction rate are the same. So when you say that a chemical reaction is at equilibrium, it is when the rate of the forward reaction, is equal to the rate of the backward reaction. So when the rate of the forward reaction is equal to the rate of the backward reaction, then you can say that the system is at equilibrium. All right? And there are two conditions that must be kept or meant by a chemical reaction for you to say that it is at equilibrium. And what are these two conditions? The first condition that must be kept is that the reaction must be reversible. That's the first condition. And the second condition is that the reaction must occur in a closed system. Must occur in a closed system. And what does that mean? When we say a reaction occurring in a closed system, it means that there is no exchange of the substances of the reaction with that of the environment, meaning that the substances within the boundary or the vessel where the chemical reaction is taking place, they are intact. They are not released to the environment, meaning that they are sealed. So it's just like you having a reaction of gases that are sealed. Of course, when gases react, when you seal them, they don't tend to escape. So it means that when you are actually carrying out the reaction in a closed system, there is no exchange of substances with that of the surrounding. All right. So when these two conditions are met by a chemical reaction, then that kind of reaction can undergo chemical equilibrium. Like I said, the word equilibrium means balance. So never should you forget that. All right. So looking at that, let's say we are given a system that is already at equilibrium, given, let's say, this reaction A plus B to give C plus D. This system is already at equilibrium, meaning it's proceeding in both directions, the forward and the backward directions. So we have reactant A, B in the forward and C, D as products, then backward reactant C, D as reactants, then A, B as products. All right. So looking at this reaction, could it be that after a reaction must have attained equilibrium, it tends to lose its equilibrium? Of course, yes. That was actually noticed by a French chemist named Henry Louis Le Chatelier. Now, this French chemist noticed that a reaction already at equilibrium has the tendency of losing its equilibrium when the reaction is subjected to some external constraints, such as changes in temperature, pressure, or concentration. Then the system tends to lose its equilibrium. But after losing its equilibrium, there is a tendency of such system trying to regain its equilibrium by adjusting itself. So that would now lead us to a principle known as the Le Chatelier's principle. The Le Chatelier's principle. And what does this principle state? The Le Chatelier's principle states that if an external constraint is imposed in a chemical system at equilibrium, such as a change in temperature, pressure, or concentration, the system would adjust itself in order to annul or to neutralize the effect of the constraint. And that adjustment of the system is to actually regain equilibrium. So what are the constraints that I mentioned? I said we have change in temperature, we have change in concentration, and we also have change in pressure. So these are the constraints that was noticed by Le Chatelier, that when these changes in constraints are imposed on a chemical system at equilibrium, the system would adjust or shift in order to annul or to neutralize the effect of the constraints, which are these ones. So we are going to look at how these different constraints tend to affect systems already at equilibrium, losing the equilibrium of the system, and the system is trying to regain the equilibrium of itself. All right, so let's see how it works. First, we will look at effect of change in temperature. Effect of change in temperature. Effect of change in temperature. Now, looking at the effect of change in temperature, we are looking at how temperature can affect a system already at equilibrium to losing its equilibrium. And what are systems that can be affected by changes in temperature? Of course, there must be reactions that are influenced upon changes in temperature. And we have two subdivisions of such reactions in the world of chemistry. We have endothermic reactions, and we have exothermic reactions. Endothermic reactions and exothermic reactions. When we talk about endo, the word endo means within, that's internal, all right? Then while the word exo means outer or external, all right? So we have endothermic and exothermic. The word thermic means heat. So endothermic reactions are simply reactions in which heat is absorbed from the surrounding. So I can say that endothermic reactions, they love heat. So when you increase the temperature of the surrounding, endothermic reactions are usually happy. They want to absorb enough heat. You get. Therefore, exothermic, they tend to release heat. So it's just like direct opposite. Endothermic absorb heat from the surrounding, while exothermic release heat to the surrounding. So can we say that exothermic reactions, they dislike heat? Of course yes, because they don't conserve heat, they don't keep heat, they dislike heat, so they tend to release heat to the surrounding, thus making the surrounding to be what? Warm or hot. Then while that of endothermic, they tend to absorb heat from the surrounding, thus making the temperature of the surrounding to be cool. You understand? So now, coming back to these reactions. For an endothermic reaction, you must have seen a reaction given. Let me use letters for simplicity. A plus B to give C plus D. And then you would see something like this. Take your delta H, which is enthalpy change, to be, let's say, negative 92 kilojoules per mole. Now looking at this delta H value that was provided is a negative value. And whenever you have a delta H value to be negative, it implies that the forward reaction is exothermic, because delta H is positive for endothermic reactions. Then while delta H value is negative for exothermic reactions. All right, so delta H value is positive for endothermic while it's negative for exothermic. So looking at this reaction now, delta H value is given to be negative. You're only interested in the sign here. Since it is negative, then it implies that the forward reaction of this reaction is actually what? Exothermic. So this is exothermic. Why? Because of the negative value. Then while the backward reaction of this reaction is endothermic automatically. So it means that when you are having the forward to be exo, then the backward should be endo. See this twist. If I happen to change this sign to plus, it means that the forward reaction here, remember I told you that this value here is always for the forward. They ought to have written it like this, but they know that so many students will understand it very easily. So they hide this one. And when they hide it, then it will be very difficult for some students to understand. But now I believe you can understand it. That this value is always for the forward reaction. So since here is positive, then automatically I'm going to erase this and write endo. Remember, endothermic, delta H is always positive. So while automatically the backward will be exo. You get the point? So that's what it means. So whenever you are having positive value of your enthalpy, which is delta H, then of course your forward reaction is endo. Then when it is negative, forward is exo. And what favors endothermic reaction? Remember I said endothermic reaction love heat. So when the temperature of the surrounding is very high, endothermic reaction is usually happy because it wants to absorb heat, it wants to gain heat. You get the point? So can we say that what favors endothermic reactions is increase in temperature? Of course yes, because when you increase the temperature of the surrounding, it favors endothermic. So an increase in temperature favors endothermic reactions. All right, then a decrease in temperature favors exothermic reactions. I'm going to explain something that's regarding this now, so please you have to be very attentive. When you say something is being favored, a part of a reaction is being favored. What does that mean? Look at this. Sometimes we already know, okay, let's take this as a case study, that our delta H value is given to be plus 92 kilojoules per mole. Now we know that our forward reaction is endo and backward is exo. And from what I have told you guys, that endothermic reaction, what favors it is increase in temperature. So if I increase temperature of this reaction, it means that the forward reaction will be favored, in that the forward is what? Endo. And what does that imply? It means that since the forward reaction is favored, equilibrium is shifting to where? To the right. And since equilibrium is shifting to the right, more of these products will be formed, meaning more of C and D will be formed. So it means favoring the forward reaction means that equilibrium is shifting to the right and more of the substances in the forward reaction are produced or formed. If you say equilibrium shifts to the left, what does that mean? Shifting to the left means that the backward reaction is favored and more of A and B are formed. That's what it means. So favoring the forward reaction, you can tell me now that it means equilibrium is shifting to the right and more of C and D are formed. Then shifting to the left, it means that more of the A and B are formed and the backward reaction is favored. So that's what it means. So if you are now asked a question from this now, what would favor the yield or the production of C and D? It's very easy. That you have to increase temperature. Why? Because your delta H is plus, and of course when it is plus, it means your forward reaction is endo, and what favors endo? Of course, there is increase in what? Temperature. So if increase in temperature favors endothermic, it means certainly more of C and D will be formed. I've already explained that before. So that's just the concept. Then what should favor the production of A and B? Of course, if backward reaction is exo, then a decrease in temperature tends to favor it. And by favoring it, it means equilibrium position is shifting to the left and more of A and B are formed. Alright, so that's just the concept about effect of change in temperature. Then let's see the next. The effect of change in concentration. The effect of change in concentration. The effect of change in concentration. Now, looking at the effect of change in concentration, when we talk about concentration, we are referring to the amount of a substance present probably in a reaction. And what does this thing really entail in terms of how it affects a system at equilibrium? Please, you have to be very attentive now. When there is an increase in the concentration of a part of a chemical reaction at equilibrium, it favors the opposite part of the reaction. Then when there is a decrease in the concentration of a part of a chemical reaction at equilibrium, it favors that same part of the reaction. What does that mean? A plus B to give C plus D. Please be very attentive now. We have two parts of this reaction. We have this part and this part. Now, if we consider this to be reactants, and we consider this to be products, usually what is opposite to reactants are the products, and what is opposite to products are the reactants. All right, so when you increase the concentration of the reactants, the products get favored. That's the implication. Then when you reduce the concentration of the reactants is favored. So it means if I increase the concentration of this reactant, the products get favored. If I increase the concentration of the products, the reactants get favored. If I reduce the concentration of the reactants are favored. If I reduce the concentration of the products are favored. You get the clear concept. So increasing this will favor this part, increasing this will favor this, reducing this will favor this, and reducing this will favor this. That's just the clear concept. So it means if I increase A and B, C and D will be produced, more of them will be produced, meaning C and D will be favored. If I reduce A and B will be favored. If I reduce C and D will be favored. If I increase C and D, A and B will be favored. You get the clear concept. So increase of this favors this, increase of this favors this, decrease of this favors this same part, and decrease of this favors this same part. That's just it. Let me also break it down for those that are maybe finding it difficult. I want to use units. Now, it's not really logical, but let me use it for simplicity purpose. Let's say we are having 1,000 units of A and B, and we are having 1,000 units of C and D. Let's say this is our equilibrium, though it's not logical because for you to say a system is at equilibrium, the rate of the forward and the backward must be the same. Not talking about the quantities, but let's use these quantities as our case study. Now, let's say having 1,000 units of A and B, having 1,000 units of C and D to be our equilibrium, meaning they are the same, balance. Picture it this way, that I increase the units of this by 200. If I increase this, it becomes 1,200, while this one is still left with what? 1,000. Has this system lost its equilibrium? Of course, yes. So now, for this system to regain equilibrium, it means that this one must shift some part of its units to this, because this is more and this is less, and this one needs more in order to regain equilibrium. So how many units should this one shift to this part in order to regain equilibrium? It's obvious it's 100 units. So if I remove 100 units from here and I shift it to this part, then it becomes 1,100, while this one will be left with 1,100 because I subtracted and I shifted to this part. So you see it now. So when I increased by 200, it was 1,200. So what part gets favored? Is it not this one? Because of course I had to shift 100 to this part. So it means this part was favored upon the increment or increase of the units of this. You understand the point? So what about, let's picture it this way, that I reduce the units of this part. Let's say I reduce this by 400 and then I'm left with 600. Let's say I just remove this 400 units and I discarded it. Then now I'm still left with 1,000 units here. So what would happen since I've already reduced the units of this in terms of concentration now? I'm left with 600, here is 1,000. The system has lost its equilibrium. So for the system to regain equilibrium, it means that this part must shift some part to this in order to get the balance, to regain balance. How many units from here should be shifted to this part in order to regain equilibrium? It's obvious that it's 200. So if I remove 200 from here and then I shift this 200 to this part, this becomes 800. This one benefited, now it has gained. Then while this one has lost, so we are still left with 800. So you observe, when I discarded 400 units, this part was still favored. You understand the point? So a reduction in the concentration of a part favors that same part. Then while an increase in the concentration of a part favors the opposite part. So that's just the concept of it. So if I increase the units or concentration of A and B, then C and D must be favored. If I increase the units of C and D, A and B must be favored. That's just the concept of concentration. And please, you have to take note of this. It could be that they are not increasing both of them. You know, I told you when you increase these two, it favors these two. It could even be that it's only one that will be increased. So let's just picture it this way, that I'm giving A plus B to give C, and I'm asked, an increase in the concentration of just A will favor what part of the reaction? C. Yes, whether it's an increase in one of the reactants or both of the reactants, the other part, the opposite part gets favored, whether one or both. So take cognizance of that. Same with that of the decrease as well. So that's about concentration, effect of changes in concentration. Then for that of the last, being effect of change in pressure. Effect of change in pressure. Of course, we know what pressure is. Pressure is the force per unit area of a system. And of course, we know that there are systems that can be affected by changes in pressure, and there are some that cannot be affected by changes in pressure, even if the system is at equilibrium. There are some systems that are at equilibrium that can never be affected by changes in pressure. So there are two conditions that a system must possess or obey in order to be affected by changes in pressure. And what are these two conditions? The first condition is that there must be at least a gaseous molecule present in the reaction. It could be the product or the reactant side. Then secondly, there must be, you see I'm laying emphasis on the must, there must be unequal gaseous volumes. There must be unequal gaseous volumes at both ends. Okay, let me just complete it. At both ends of the reaction. All right, there must be unequal gaseous volumes at both ends of the reaction. So if a system wants to be affected by changes in pressure, then that system must obey these two principles, not in obedience to one and in disobedience to another. No, the system must be in obedience to both of them. All right, so let's see how we can actually obey these principles. You can actually pause the video and quickly take down this stuff. So looking at this system, let's say we are given N2 gas plus H2 gas, then to give NH3 gas. Then balancing this reaction, here will be 3, here will be 2. The reaction is balanced. You check. We have 2 nitrogen, then hydrogen is 6, here is 6. So everything is balanced. This is known as Haber process. That is the industrial manufacturing of ammonia. All right, so looking at this reaction, can this reaction be affected by changes in pressure? Let's confirm. You know the first principle, there must be at least a gaseous molecule in the reaction. And looking at this reaction, we have all of them to be gases, so it's very, very sweet that this reaction has obeyed the first principle. Then the second condition is that they must have unequal gaseous volumes. Let's confirm. The volume of nitrogen gas here is 1 volume, meaning 1, this is assumed to be 1. Then this is 3 volumes of hydrogen, then while this one is 2 volumes of ammonia. So when you sum up, this becomes 4 volumes in the reactant side and 2 volumes in the product side. So it means since they are having unequal, the numbers are different, 4 and 2. Then you can say that this system has obeyed the second condition, and of course it can be affected by changes in pressure. Take a good look at this one. H2 gas plus Cl2 gas to give HCl gas. Observe this reaction. The reaction is balanced. We have 2 atoms of hydrogen, 2 chlorine, everything is balanced. But can this system be affected by changes in pressure? Let's confirm. In obedience to the first principle, the first principle has it that you are having, we are having gases all through. So of course it has obeyed the first principle. Then what about the second principle? There must be unequal gaseous volumes. Let's confirm. The volume of gas here is 1 volume, then this one is 1 volume. But in this case it's 2 volumes. You see it now? So when you sum up this, it gives 2 volumes, while this still remains 2 volumes. So since the volumes are the same, then this system cannot be affected by changes in pressure, meaning that the system remains unaffected by changes in pressure, while it obeyed the first and disobeyed the other. So like I said, the system that must be affected by changes in pressure must obey the 2 principles. All right? So let's quickly see how changes in pressure can affect a system at equilibrium, such as this. Now, an increase in pressure favors the part of the reaction with the smaller gaseous volume, while a decrease in pressure favors the part of the reaction with with the bigger gaseous volume. All right. So the hint here that you can use to always remember this is Boyle's law. Boyle's law: the volume of a given mass of gas is inversely proportional to what? To its pressure. Take a good look at this. You know, in Boyle's law chart, you are having something like this: pressure, 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 then volume, volume, volume. Observe, when you are moving to this direction, a decrease in the size of P is resulting in an increase in the size of V. Then while a decrease in the size of V is resulting in an increase in the size of P. There's an inverse relationship between volume and pressure in Boyle's law, meaning an increase in volume favors a decrease in pressure, while a decrease in volume favors an increase in pressure. So always have this at the back of your mind when you are attempting questions on that, that an increase in pressure will favor the part with what? With the lower gaseous or smaller gaseous volume, meaning when you increase pressure, you favor small volume. When you reduce pressure, you favor big volume. You get the point? So you are now asked the question: what will favor the forward direction? What will favor the forward direction? Now check the volumes. Say this is 4 volume and this is 2 volume. Forward direction is to 2 volume. So if forward direction is to 2 volume, then it means that there must be an increase in pressure to favor this part, because this is bigger volume, this is smaller volume, and like I said, what favors the part with the smaller volume is when you increase pressure. Then coming backward, we have the bigger volume here. So bigger volume should be favored by what? Smaller pressure. So when you decrease pressure, it favors the backward reaction. Remember what I said before, that favoring forward or backward, it means the substances at both directions will be favored or will be produced in excess. So in this case now, favoring the forward reaction means that more ammonia will be obtained or formed. The favoring backward reaction means that more nitrogen and hydrogen will be produced or formed. So that's just the concept. So imagine you ask a question on this: what will favor the yield of ammonia? Where can you find ammonia? That's the first question you should ask yourself. Is it at the backward or at the forward? So obviously it's at the forward. So since ammonia is present at the forward, then what will favor it in terms of changes in pressure? Is it an increase or a decrease? Check the volumes. This is 4 volumes, this is 2 volumes. So now, since this one has a lower volume to the part of ammonia, then of course there is need to apply a high pressure to favor that part. Why? Because an increase in pressure favors the part of the reaction with the smaller volume. That's just the concept. All right. So there is a miscellaneous question that I'll be dropping, and I would want you to, give me your suggestion on it. Maybe I will just give, like, let's say, some seconds for me to see whether you guys understand. On the board, we are having the question. Now, this is still a Haber process, no doubt. We still have other processes like the contact process and the rest. We can still check for some questions on that too. All right. Now, looking at this question, just take a deep breath and try to see how you can figure out this, the answer to the question. Take like 20 to 30 seconds. I believe some smart ones won't even waste time getting the answer to this. But let's see. In this kind of question, you have to be very careful because you are having diverse constraints here. So you have to be very, very careful. Looking at the reaction, they said, given the reaction below, this is the reaction, and you were giving your delta H value to be negative, what will favor the yield of ammonia? You see, they did not write what will favor the yield of NH3. You see how this question is kind of tricky. So if your ammonia is N2, then of course you know what you're supposed to do there. Then it means that you get a very wrong value. So looking at this, your ammonia is NH3. That's the formula of ammonia. So we are looking at what will favor the forward reaction, meaning the yield of ammonia. Going by temperature as option A, our delta H value here is given to be minus 46.1 kilojoules per mole. We are not interested in the value, just the sign. So since this sign is negative, then it implies that the forward reaction is what? Is exo. Yes, because of negative. Then the backward automatically will be what? Endo. Good. Now, going by changes in temperature, remember, a decrease in temperature favors the forward reaction based on the fact that the forward is exo. And what favors exo is decrease in temperature. So of course they said increase in temperature, and we are interested in the forward reaction here now. That's what we're interested in. So this is wrong. Then the next, decreasing the pressure. Let's see. In terms of, let's check whether the reaction can be affected by changes in pressure. We've done that before, but let's just confirm. Now we have gases in obedience to the first principle, and the second, the total volumes here is what, 4. That's 1, 3, 4. Then this is 2. So this is 4 volume and this is 2 volume. So in this case, what will favor this forward? Because we are interested in the ammonia production now. So the forward is, we have the lower volume here. And what favors the part with the lower volume is when you increase pressure. So an increase in pressure favors the part with the smaller volume, and they said decreasing pressure, so this is still wrong. Then addition of catalyst, this is very wrong, very, very wrong. I had to even strike it twice. Why? Because catalyst does not affect systems at equilibrium. What catalyst does is that it tends to bring about a speed with which the equilibrium is reached or attained. So it doesn't affect any form of production of any parts of the reaction. All right. So that's very, very wrong. Then D, let's confirm D. Removal of some NH3. Remember, NH3 still remains our ammonia, no doubt. That's our ammonia. So removal of some NH3 during its formation. Let's confirm something. This is taking us to our constraint known as concentration. And remember what I said. When you decrease concentration of one part, it favors that same part. Remember? So removal of some NH3, meaning you are decreasing the concentration of some part of this. And what part will still be favored in the process? It's still the same part. So what will favor the yield of this part is when you decrease the concentration of this part. So a decrease in the concentration of this favors this same part. An increase in the concentration of these two favors this same part. This part. Then a decrease in the concentration of this favors this same part. You understand the point? So when you decrease concentration here, it favors this same part. When you increase the concentration of this, it favors these two. When you increase the concentrations of these two, it favors this. When you decrease the concentration of these two, it favors this same two. All right? You can actually maybe take the video back and watch that part where I explained effect of changes in concentration. All right? So the correct answer is this. Why? Because when you remove some part of this, more of it will still be formed in the process. So this becomes the answer. We still have other processes that are affected by changes in temperature, pressure, concentration, like in the contact process. The most relevant step of contact process is when sulfur 4 oxide reacts with oxygen, or it bonds in oxygen to produce sulfur 6 oxide, which is contact process. And balancing this reaction, you have something like this. Now, you might be giving your delta H value to be negative. All right. So if just picture it this way, that this reaction, you are giving your delta H value to be negative, and you are told what will favor the formation of sulfur 6 oxide in terms of changes in temperature. Of course, now this is indicating that this is exo. So what will favor exo is not decrease in temperature. Of course, yes, that will not favor this production. So just try as much as possible to rewatch this video so as for you to get the clear concept of the Le Chatelier's principle. All right. Then we still have other things that we need to. This video lesson will be split into 3 parts. We are in the first part. We are done with the first part. So we are still having 2 more parts talking about the derivation of equilibrium constants that was postulated by 2 scientists, Cato Goodberg and Peter Wedge. These were the 2 scientists that came up with the idea of the law of mass action in the postulation of chemical equilibrium constants. And we are going to look at that in our next video. Then we are still going to be having more videos on calculations involving chemical equilibrium in terms of the constants and all that. So it's my hope that you've been able to understand this very well. And don't forget to like the video if you like it. Just place your thumbs up there. And you can actually comment, place your comments anywhere you are not clear. You can drop your comment, and then you can share the videos, as well as informing your friends about the channel, because we still have quite a number of things to learn together. Thanks for watching, and don't forget to subscribe. Stay tuned, and God bless.